Hello, it's Eric Topol with Ground Truths, and I am really thrilled to have with me Professor Faisal Mahmood, who is lighting it up in the field of pathology with AI. He is on the faculty at Harvard Medical School, also a pathologist at Mass General Brigham, and with the Broad Institute. And he has been publishing at a pace that I just can't believe. We're going to review that in chronological order. So, welcome, Faisal.
Thank you so much for having me, Eric. I do want to mention I'm not a pathologist. My background is in biomedical imaging and computer science. But yeah, I work very closely with pathologists both at Mass General and at the Brigham. Yeah.
Okay, well, you know so much about pathology. I just assumed that you were actually, but you are taking computational biology to new levels, and you're in the pathology department at Harvard. I take it, right?
Yeah, I'm at the pathology department at Mass General Brigham. So the two hospitals are now integrated. So I'm at the joint department.
Good. Okay. Well, I'm glad to clarify that because, as far as I knew, you were, hardcore pathologist. So you're changing the field in a way that is quite unique, I should say, because a number of years ago, deep learning was starting to get applied to pathology, just like it was in radiology and ophthalmology, and we saw some early studies with deep learning, whereby you could find so much more on a slide that otherwise would be not even looked at or considered, or even that humans wouldn't be able to see. So maybe you could just take us back first to the deep learning phase before these foundation models that you've been building, just to give us a flavor for what was the warm up in this field.
Yeah. So I think around 2016 and 17, it was very clear to the computer vision community that deep learning was really the state of the art, where you could have abstract feature representations that were rich enough to solve some of these fundamental classification problems in conventional vision. And that's around the time when deep learning started to be applied to everything in medicine, including pathology. So we saw some earlier studies in 2016 and 17, mostly in machine learning conferences, applying this to very basic, patch level pathology data sets. And then in 2018 and 2019, there were some studies in major journals, including in Nature Medicine, showing that you could take large amounts of pathology data and classify what's known to us, and including predicting what's now commonly referred to as non-human identifiable features, um, where you could take a label, and this could come from molecular data, other kinds of data like treatment response and so forth, and use that label to classify these images as responders versus non-responders, or having a certain kind of a mutation or not. And what that does is that if there's a morphologic signal within the image, it would pick up on that morphologic signal, even though humans may not have picked up on it.
Right.
So it was a very very exciting time of developing all of these supervised foundation models. And then I started working in this area around 2019. And one of the first studies we did was to try to see if we can make this a little bit more data efficient. And that's the CLAM method that we published in 2021. And then we took that method and applied it to the problem of cancers of unknown primary. That was also in 2021.
Yeah. So just to review, in the phase of deep learning, which was largely, we're talking about supervised with ground truth images, there already was a sign that you could pick up things like the driver mutation, the prognosis of the patient from the slide. You could, structural variations, the origin of the tumor, things that would never have been conceived as pathologists. Now, with that, I guess the question is, was all this confined to whole slide imaging, or could you somehow take an H&E slide, conventional slide, and be able to do these things uh, without having to have a whole slide image?
Right. So At the time, most of the work was done on slides that were fully digital. So taking a slide and then digitizing the image and creating a whole slide image. But we did show in 2021 that you could put the slide under a microscope and then just capture it with a camera or just with a cell phone coupled to a camera, and then still make those predictions. So these models were quite robust to that kind of domain adaptation, and still I think that even today, um, the slide digitization rate in the U.S. remains at around 4%, and the standard of care is just looking at a glass slide under a microscope. So it's very important to see how we can further kind of democratize these models by just using the microscope. Because most microscopes that pathologists use do have a camera attached to them. So how can we somehow leverage that camera to just use a model that might be trained on a whole slide image, still work with the slide under a microscope?
Well, what you just said is actually a profound point. That is, only 4% of the slides are being reviewed digitally. And that means that we're still in old pathology era without the enlightenment of machine eyes. I mean, these digital eyes that can be trained um, even without supervised learning, as we'll get to see things that we'll never see, and to make and you, I know, will be recalling back in 2022, you and I wrote a Lancet piece
Yeah.
about the work that you had done, which is very exciting, with cardiac biopsies to detect whether a heart transplant was a rejection. This is a matter of life or death because you have to give more immunosuppression drugs if it's a rejection. But if you do that and it's not a rejection or you miss it, it's and there's lots of disagreement among pathologists, cardiac pathologists, regarding whether there's a transplant. So you had done some early work back then, and because much of what we're going to talk about, I think, relates more to cancer, but it's across the board in pathology. Can you talk about the inner observer variability of pathologists when they look at regular slides?
Yeah. So when I first started working in this field, my kind of thinking was that the slide digitization rate is very low. So how do we get people to embrace and sort of adapt digital pathology and machine learning models that are trained on digital data if the data is not routinely digitized? So one of the you know my kind of line of thinking was that if we focus on problems that are inherently so difficult, like that there isn't a good solution for them currently, and machine learning provides or deep learning provides like a tangible solution, people would be kind of forced to use these models. So along those lines, we started focusing on the cancers of unknown primary problem and the endomyocardial biopsy uh, problem, right? So we know that the Cohen's kappa, or the intra-observer variability that also takes into account agreement by chance, is around 0.22. So it's very, very low for endomyocardial biopsies. So that just means that there are a large number of patients who have a diagnosis that other pathologists might not agree with. And the downstream treatment regimen that's given is entirely based on that diagnosis. The same patient being diagnosed by a different cardiac pathologist could be receiving a very different regimen and could have a very, very different outcome.
Right.
Um, so the goal for that study, is published in Nature Medicine in 2022, was to see if we could use deep learning to standardize that, um, and have it act as an assistive tool for cardiac pathologists, and whether they give more standardized responses when they're given a machine learning based response. So that's what we showed, and it was a pleasure to write that corresponding piece with you in the Lancet. Yeah.
Yeah, no, I mean, I think that was 2 years ago, and so much has happened since then. So now I want to get into this. You've been on a tear every month, publishing major papers in leading journals. And I want to just go back to March, and we'll go talk about April, May, and June. So back in March, you published two foundation models Uni and Conch, I believe, both of these and back-to-back papers in Nature Medicine. And so maybe first, if you could explain, the foundation model, the principle, how that's different than the deep learning network in terms of transformers, and also what these two different, these were mega models that you built, how they contributed to help advance the field.
Yeah. So a lot of the early work that we did relied on extracting features from a ResNet trained on real world images. So by having these features extracted, we didn't need to train these models end to end, and allowed us to train a lot of models and investigate a lot of different aspects. But those features that we used were still based on real world images. What foundation models let us do is that they leverage self-supervised learning and large amounts of data that would be essentially unlabeled, to extract rich feature representations from pathology images that can then be used for a variety of different downstream tasks. So we basically collected as much data as we could from the Brigham and MGH and some public sources, while trying to keep it as diverse as possible. So the goal was to include infectious, inflammatory, neoplastic, all everything across the pathology department, while still being as diverse as possible, including normal tissue,
Mm.
everything. Um, and the hypothesis there, and that's been just recently confirmed, that the hypothesis was that diversity would matter much more than the quantity of data. So if you have lots and lots of screening biopsies and you use all of them to train the foundation model, there isn't enough diversity there that it would begin to learn those fundamental feature representations that you would want it to learn. So we used all of this data and then trained the uni model, and then together with it was an image text model where it starts with uni and then reinforces the feature representations using images and text, and that sort of mimics how humans learn about pathology. So a new resident, new trainee learning pathology has a lot of knowledge of the world, but is perhaps looking at a pathology image for the first time. But besides looking at the image, they're also being reinforced by all these language cues, from whether it's from text or from audio signals. Um, so the hope there was that text would kind of reinforce that and generate better feature representation. So the two studies were made available together. They were published in Nature Medicine back in March, and with that, we made both those models public. So at the time, we obviously had no idea that they would generate so much interest in this field. They've been downloaded over 350,000 times on Hugging Face and used for all kinds of different applications that I would have never thought of. So that's been very exciting to see.
Can you give some examples of some of the things you wouldn't have thought of? Because it seems like you think of everything.
Yeah, so people have used it to win a challenge. There was a challenge for detecting tuberculosis. I think in a very very different kind of a data set. It was from the Nightingale Foundation, and they have
Mm.
large data sets. So that was very interesting to see. People have used it to create newer data sets that can then be used for training additional foundation models. It's being used to um, extract rich feature representations from pathology images corresponding spatial transcriptomic data, trying to predict spatial transcriptomics directly from histology. And there's a number of other
Sure.
options.
Well,
Um,
yeah. Before we get to that was March. Before we get to April, you slipped in the spatial omics thing, which is a big deal. That is, ability to look at um, tissue, human tissue, time over time and space. I mean, the spatial temporal. It will tell us so much, whether it's an evolution of a cancer process or so many things. Can you just comment, because this is one of the major parts of this new era of applying AI to biology?
Yeah, so I think that there is there are a number of things we can do. If we have spatial data, spatially resolved omic data with histology images, right? So the first thing that comes to my mind as like a computer scientist would be that can we train like a joint foundation model where we would use the spatially resolved transcriptomics to further enforce the pathology signal as a ground truth in a contrastive manner, similar to what we do with text. And can we use that to extract even richer feature representation? So we're doing that. In fact, we made a data set of about 1,000 pathology images with corresponding spatial transcriptomic uh, information, both curated from public resources as well as some internal data publicly available, so people could investigate that question further. Um, we're interested in like other aspects of this because there is some indication, including a study from James Zhao's group at Stanford, showing that we can predict histology, predict the spatial transcriptomic signal directly from histology. So there's early indications that we might also be able to do that in 3 dimensions. So there, yeah, it's definitely very interesting. More and more of that data is becoming available, and how machine learning can sort of augment that is very exciting. Yeah.
Yeah, I mean, so most of the spatial omics has been a product of single cell sequencing, whether it's single nuclei and different omics, not just DNA, of course, RNA and even methylation and whatnot. So the fact that you could try to get impute that from the histology is pretty striking. Now, that was March. And then in April, you published to me an extraordinary paper about demographic bias and how generative AI, we're in the generative AI era now, since there, as we discussed with foundation models. Here again, that Gen AI could actually reduce biases and enhance fairness, which of course is so counterintuitive to everything that's been written to date. So maybe you can take us through how um, we can get a reduction in bias in pathology.
Yeah. So in the study was about what was this had been investigated in other fields. But what we try to show is that what a model trained on large, diverse, publicly available data, when that's applied internally, and we stratify it based on demographic differences, race, and so forth, we see these very clear disparities and biases, right? And we investigated a lot of different solutions that were out there to equalize the distribution of the data, to balance the distribution using oversampling and some of these simple techniques, and none of them worked quite well. Um, and then we observed that using foundation models or just having richer feature representations eliminates some of those biases. In parallel, there was another study from Google where they used generative AI to synthesize additional images from those unrepresented groups and then use those images to enhance the training signal. And then they also showed that you could reduce those biases. So I think the common denominator there is that richer feature representations contribute to reduced biases. So the bias is not because that there's some inherent signal tied to these subgroups, but the bias is essentially there because the feature representations are not strong enough. Another general observation is that there's some kind of a confounder often there that leads to the bias. And one example would be that patients with socioeconomic disparities might just be diagnosed late, and there might not
Mhm.
be enough advanced cases in the training data set. So quite often when you go in and look at what your training distribution looks like and how it varies from your test distribution and what that data set shift is, you're able to figure out where the bias inherently comes from. But as a general principle, if you use the richest possible feature representation or focus on making your feature representations richer by using better foundation models and so forth, you're able to reduce a lot of the bias.
Yeah, well, that's a really another key point here is about the richer features. and the ability, counterintuitively, to actually reduce bias, and what is important in interrogating data inputs, as you said, before you wind up with a problem with bias. Now, then it comes May, since we're just March and April. May, you published TriPath, which is now bringing in the 3D world of pathology. So maybe you can give us a little skinny on that one.
Yeah. Just looking at the spectrum of where pathology is today, I think that we all sort of agree in the community that pathologists often look at like extremely sampled tissue. So human tissue is inherently three-dimensional, and by the time it gets to a pathologist, it's been sampled and cut so many times that it sort of often would lack that signal. And there are a number of studies that have shown that if you subsequently cut sections, you get to a different outcome. If you look at multiple slides for a prostate biopsy, you get to a different Gleason score. There are all of these studies that have shown that 3D pathology is important. And with that, there's been a growing effort to build tools, microscopes, imaging tools that can image tissue in 3D. And there are about 10 startups who've built all these different technologies, open top light sheet microscopy, micro CT, and so forth, that can image tissue really well in 3 dimensions. But none of them have had clinical adoption. And we think that a key reason is that there isn't a good way for a pathologist to examine such a large volume of tissue. If they spend so much time examining this large volume of tissue, they would never be able to get through all the
All right.
cases, right? So the goal here really was to develop a computational tool that would look through the large volume and highlight key regions that a pathologist can then examine. And the secondary goal was that does using three-dimensional tissue actually improve patient stratification, and does using essentially using 3D deep learning, having 3D convolutions, extract richer features from the 3 dimensions that can then be used to separate patients into distinct risk groups. So that's what we did in this particular case. The study relied on a lot of data from Jonathan Liu's group at University of Washington, and also data that we collected at Harvard, from tissue that came from the Brigham and Women's Hospital. So it was a very exciting to show what the value of 3D pathology can be, and how it can actually translate into the clinic using some of these computational tools.
And do you think ultimately someday that will be the standard, that you'll have a 3D assessment of a biopsy sample?
Yeah, I'm really convinced that ultimately 3D would become the standard, because the technology to image these tissue is becoming better and better every year, and it's getting closer to a point where the imaging can be fast enough to get to clinical deployment. And then on the computational end, we're increasingly making a lot of progress.
And it seems, again, it's something that human eyes couldn't do, because you'd have to look at hundreds of slides to try to get some, you know, loose sense of what's going on in a 3D piece of tissue. Whereas here, you're again taking advantage, exploiting the digital eyes. Now, this culminates to your June big paper, Path Chat in Nature. And this was a culmination of a lot of work you've been doing. I don't know if you do any sleep, or your team, but then you published a really landmark paper. Can you take us through that?
Yeah, so I think that with the foundation models, we could extract very rich feature representation. So to us, kind of the obvious next step was to take those feature representations and link them with language. So um, a human would start to communicate with a generative AI model, where we could ask questions about what's going on in a pathology image. It will be capable of making a diagnosis. It will be capable of writing a report. All of those things. And the reason we thought that this was really possible is because pathology knowledge is a subset of the world's knowledge, right? And companies like OpenAI are trying to build singular multimodal large language models that would harbor the world's information, the world knowledge. And pathology is much, much more finite. And if we have the right kind of training data, we should be able to build a multimodal large language model that, given any pathology image, it can interpret what's going on in the image. It can make a diagnosis. It can, run through grading, prognosis, everything that's currently done, but also um, be an assistant for research, analyzing lots of images to see if there's anything common across them, cohorts of responders versus non-responders and so forth. So we started by collecting a lot of instruction data. So we started with the foundation models. We had strong pathology image foundation models. And then we collected a lot of instruction data where we have images, questions, corresponding answers. And we really leveraged a lot of the data that we had here at Brigham and MGH. We're obviously teaching hospitals. There were questions to existing teaching training materials, um, and work closely with pathologists at multiple institutions to collect that data, and then finally trained uh, 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 a multimodal large language model where we could give it a whole slide image, start asking questions what was in the image, and then it started generating all these interesting morphologic descriptions. But then the challenge, of course, is that how do you validate this? So then we created validation data sets, validated it on multiple choice questions, on free flowing questions where multiple pathologists, we had a panel of 7 pathologists, look through every response from our model as well as more generic models like the OpenAI GPT-4 and Biomed Clip and other models that are publicly available, and then compare how well this pathology specific model does in comparison to some of those other models, and we found that it was very good at morphologic description.
It's striking though to think now that you have this large language model where you're basically interacting with the slide, and um, that this is rich. But in another way, just to ask you, we talk about multimodal, but what about if you have the electronic health record, the person's genome, gut microbiome, the immune status, and social demographic factors, and all these layers of data, environmental exposures, and the pathology. Are we going to get to that point eventually?
Yeah, absolutely. So that's what we're trying to do now. So I think that it's obviously one step at a time. There are some data types that we can very easily integrate, and we're trying to integrate those and really have PathChat as being like a binder to all of that data. And pathology is a very good binder because pathology is medicine's ground truth. A lot of the fundamental decisions around diagnosis and prognosis and treatment trajectory is all sort of made in pathology. So having everything else bind around the pathology is a very good uh, idea and indication, right? So for some of these data types that you just mentioned, like electronic medical records and radiology, we could very easily, do go that next step and make and build integrative models, both in terms of building the foundation model and then linking with language and getting it to generate responses and so forth. And for other data types, we might need to do some more specific training data types that we don't have enough data to build foundation models and so forth. So we're trying to sort of expand out to other data types and see how pathology can act as a binder. Yeah.
Well, if anybody's going to build it, I'm betting on you and your team there, Faisal. Now, what this gets us to is the point that 90 was it 96% or 95% of pathologists in this country are basically in an old era. We're not, eking out so much information from slides that they could. And here you're kind of in another orbit. You're in another world here, whereby you're coming up with information. I mean, things I never would have thought, like, really the prognosis of a patient over an extended period of time, the sensitivity of drugs to the tumor from the slide, no less the driver mutations to be able to, so you wouldn't even have to necessarily send for mutations of the cancer because you get it from the slide. There's so much there that isn't being used. It's just, to me, unfathomable. Can you help me understand why the pathology community now that I know you're not actually a pathologist, but you're actually trying to bring them along. What is the reason for this resistance? Because there's just so much information here.
Yeah. So there are a number of different reasons. I mean, if you go into details for why digital pathology is not actively happening, um, there just digitizing an entire department is expensive. Retaining large amounts of slides is expensive, um, and then the the value proposition in terms of patient care is definitely there, but the financial incentives, reimbursement around AI is not quite there yet. It's slowly getting there, but it's not quite there yet. In the meantime, I think what we can really focus on, and what my group is sort of thinking a lot about, is that how can we democratize these models by using what the pathologists already have. And they all have a microscope, and most of them have a microscope with a camera attached to it. Can we train these models on whole slide images like we have them, and adapt them to just um, a camera coupled to a microscope, and that's what we have done for PathChat too. I think one of the demos that we showed after the article came out was that you could use PathChat on your computer with the whole slide image, but you can also use it with a microscope just coupled to a camera, and you put a glass slide underneath. And in an extreme lower source setting, you can also use it with just a cell phone coupled to a
Mm,
microscope.
mm.
We're also building a lighter weight version of it that wouldn't require internet, so it would just be completely locally deployed. And then it could be, active in lower source settings where sometimes sending a consult can take a really long time, and quite often it's not very easy for hospitals in lower source settings to track down a patient again once they've actually left, because they might have traveled a long distance to get to the clinic and so forth, right? Um, so the value of having PathChat deployed in a lower source setting where it can run locally without internet is just huge, because it can accelerate the diagnosis so much. In particular for very simple things, which is like very good at making a diagnosis for those cases.
Oh, sure, and you can help bridge inequities, and I mean all sorts of things that could be an outgrowth of that. But what I still having a problem with, from the work that you've done, and some of the other people that you know well that are working assiduously in this field, if I had a biopsy, I want all the information. I don't want to just have the old, I would assume you feel the same way. I mean, we're not helping patients by not providing the information that's there just with a little help from AI. What if it's going to take years for this to transformation to occur, a lot of patients are going to miss out because their pathologists are not coming along.
Yeah, yeah, yeah. I think that one way to, of course, solve this would be to have it congressionally mandated, like we had for electronic medical records.
Mm, mm.
Um, and there are other arguments to be made. That, I mean, it's been the case for a number of different hospitals have been sued for losing slides. So if you digitize all your slides, and you're not going to lose them. Um, the but I think it will take time. So a lot
Yeah.
of hospitals are making these large investments, including here at the Brigham and MGH. But it will take time for uh, all the scanners, all the storage solutions, everything to be in place. And then it will also take time for pathologists to adapt. So a lot of pathologists are very excited about the new technology, but there are also a lot of pathologists who feel that their entire career has been diagnosing cases, or using a microscope and slides. So it's too big of a transition for them. So I think there'll obviously be some transition period where both would coexist, and that's happening at a lot of different institutions. And eventually, I think everything will be digital.
Yeah, I get what you're saying, Faisal, but when I wrote Deep Medicine and I was studying what was the pathology uptake then of deep learning, it was about 2%. And now it's
Yeah,
5 years later and it's, 4% or 5% or whatever. This is glacial type, evolution. This is not keeping up with how the progress that's been made. Now, the other thing I just want to ask you before finishing up, there are some AI pathology companies like Path AI. I think you have a startup, Medela AI. But what can the companies do when there's just so much reluctance to go into the digital era of pathology?
Yeah. So I think that this has been a big barrier for most pathology startups because around 7 to 8 years ago when most of these companies started, the hope was that digital pathology would happen much faster than it actually has. Um, so I think one thing that we're sort of doing at Modella is that we understand that the adoption of digital pathology is slow. So everything that we're building, we're trying to enable it to work with the current solutions that exist, right? So a pathologist can capture images from a pathology slide right in their office with a camera with a microscope, and PathChat, for example, works with that. And then the next sort of series of tools that we're developing around agentic AI would also be developed in a manner that it would be possible to use um, just a camera coupled to a microscope.
Mm,
Uh,
mm.
so I think that I do feel that the all of these pathology AI companies would have been sort of doing much better if everything was digital, because adopting the tools that they developed would be very straightforward. Right now, the barrier is that even if you want to deploy an AI driven solution, if your hospital is not entirely digital, it's not possible to do that. So it requires this huge upfront investment.
Yeah,
Um,
no, it's extraordinary to me that this is a such an exciting time, and it's just not getting actualized like it could. Now, if somebody who's listening to our conversation um, has a relative or even a patient or whatever that has a biopsy and would like to get an enlightened interpretation with all the things that could be found that are not being detected, um, what is there a way to send that to a center that is uh, facile with this, or is this if that's a no go right now?
so I think at the moment it's not possible, and the reason is that a lot of the generic AI tools are not sort of ready for this. The models are very specific for specific purposes. The generalist models are just getting started, but I think that in the years to come, this would be a competitive edge for institutions who do adopt AI. They would definitely have a competitive edge over those who do not. Um, we we do from time to time receive requests from patients who want us to run their slides on the cancers of unknown primary tool that we built, and it depends on whether we are allowed to do so or not, because it has to go through a regular diagnostic first, and how much information can we get from the patient, but it's on a case by case basis.
Well, I hope that's going to change soon because you have been, your team there has just been working so hard to eke out all that we can learn from a path slide, and it's extraordinary. And it made me think about what we knew 5 years ago, which already was exciting, and you've taken that to the fifth power now, so, or whatever. So anyway, just to congratulate you for your efforts. I just hope that it will get translated, Faisal.
Yeah.
I'm very frustrated to learn how little this is being adopted here in this country, a rich country, which is ignoring the benefits that it could provide for patients.
Yeah. Yeah, that's our goal over the next or the next 5 years. So the hope really is to take everything that we have developed so far and then get it in sort of aligned with where the technology currently is, and then eventually deploy it both at our institution and then across the country. So we're working hard to do that.
Well, maybe patients and consumers can get active about this and demand their medical centers to go digital instead of living in
Absolutely,
an analog glass slide world, right? Um,
absolutely.
yeah, maybe that's the route. Anyway, thank you so much for reviewing. This pace of your publications is pretty much unparalleled, not just in pathology AI, but in many parts of life science. So, kudos to you, Richard Chen, and your group, and so many others that have been working so hard to enlighten us. So, thanks. I'll
Yeah,
be checking in with you again on whatever the next model that you build, because I know it'll be another really important contribution.
thank you so much, Eric. Thanks.